We previously studied the fundamental concepts of amplifier circuits, circuit models, and primary performance metrics. Now we will discuss integrated circuit operational amplifiers, commonly abbreviated as op-amps. An electrical circuit with a specific function fabricated on a small silicon die is called an integrated circuit. Integrated circuits offer advantages such as powerful functionality, small size, low power consumption, high reliability, and excellent cost performance. They are widely used in linear circuits for signal amplification, computation, and conversion, and can also be employed in switching circuits. Since we have not yet studied transistor circuits, we will not go into the internal circuitry of integrated op-amps here. Instead, we will regard the op-amp as a black box, focus on its port characteristics, and leave its internal circuit for later. The internal structure of an integrated op-amp can be broadly divided into three parts: an input stage, an intermediate stage, and an output stage. The input stage primarily addresses drift suppression and effective amplification of the signal. The main task of the intermediate stage is to greatly increase the voltage gain. The main task of the output stage is to enhance load driving capability. The circuit has two input terminals: the non-inverting input P, positive, and the inverting input N, negative, denoted by plus and minus, respectively, and one output terminal O, output. Their voltages with respect to ground are denoted V sub P, V sub N, and V sub O, respectively. When only terminal P is driven with an input V sub P, with V sub N equals 0, the output voltage V sub O is in phase with V sub P. When only terminal N is driven with an input V sub N, with V sub P equals 0, V sub O is inverted relative to V sub N. V sub plus and V sub minus are the positive and negative supply terminals, respectively. From the perspective of signal amplification, the input stage amplifies the voltage difference between inputs P and N, i.e., V sub O1 equals A sub V1 times the quantity V sub P minus V sub N, where A sub V1 is the voltage gain of the input stage. After V sub O1 is further amplified by the intermediate and output stages and delivered to the output, V sub O equals A sub VO times the quantity V sub P minus V sub N, where A sub VO is the overall voltage gain of the integrated op-amp. Thus, it can be seen that the function of an op-amp is to amplify the difference between the two input voltages. There are two commonly used graphical symbols for operational amplifiers. The one on the left is the national standard symbol, and the one on the right is the commonly used symbol. In these symbols, the triangle indicates that the signal flows from left to right, and in both symbols the power supply terminals are not shown. Circuit model of the operational amplifier. As we learned in Chapter 1, when the specific structure and parameters of an amplifier circuit are unknown, we can study the amplifier by constructing a circuit model. The figure shows a simplified port model of an amplifier from the perspective of the signal source. Everything following it is its load, and the op-amp's input port is equivalent to an input resistance R sub I. From the perspective of the load, everything preceding it is effectively a source. So the output port is equivalent to an output resistance R sub O in series with a controlled voltage source A sub VO times the quantity V sub P minus V sub N. The supply voltages V sub 1 and V sub 2 provide the op-amp with positive and negative operating voltages, respectively. Power supplies are essential for an op-amp to operate. For simplicity, supply circuitry is usually omitted from schematic diagrams and drawn only when necessary. Unless otherwise specified, all op-amp circuits herein are assumed to use symmetrical dual supplies. The controlled voltage source A sub VO times the quantity V sub P minus V sub N is controlled by the voltage difference between the non-inverting and inverting terminals. Here A sub VO is the open-loop voltage gain, and A sub VO is greater than 0. For integrated op-amps, A sub VO is relatively high, typically exceeding 10 to the power of 5. The input resistance R sub I is also high, typically reaching 10 to the power of 6 ohms, whereas the output resistance R sub O is small, less than 100 ohms. Transfer characteristics of the operational amplifier. The output voltage V sub O is limited by the positive and negative supply voltages, i.e., V sub minus is less than or equal to V sub O. When A sub VO times the quantity V sub P minus V sub N greater than or equal to V sub plus, V sub O equals V sub plus. The value of VO will not increase further with an increase in V sub P minus V sub N and can only remain at the supply value V sub plus. When A sub VO times the quantity V sub P minus V sub N less than or equal to V sub minus, V sub O equals V sub minus. The op-amp enters saturation, and the functional relationship between V sub O and V sub P minus V sub N no longer holds. The relationship between V sub O and V sub P minus V sub N can be described by a voltage transfer characteristic curve. As shown in the figure, the op-amp's voltage transfer characteristic can be divided into 3 segments. The middle portion is the linear operating region, in which V sub O equals A sub VO times the quantity V sub P minus V sub N, with the slope equal to A sub VO. Only when V sub P minus V sub N is within a very small range can the op-amp be ensured to operate in the linear region. As V sub P minus V sub N increases, the characteristic curve flattens into a horizontal line due to the limitations imposed by the supply voltages, and the output no longer maintains a linear relationship with the input. V sub O reaches the saturation value of V sub plus or V sub minus. In practice, because the internal transistors of the op-amp consume a portion of the voltage, the maximum output voltage is usually less than the positive supply voltage, and the minimum output voltage is greater than the negative supply voltage. Given that the open-loop gain A sub VO of the op-amp is very high, even a very small voltage difference is sufficient to drive the output into saturation. Therefore, measures are taken to reduce the op-amp's gain. Output current of the operational amplifier. When the op-amp output is connected to a load and V sub O greater than 0, current flows out of the output and into the load R sub L. When V sub O less than 0, current flows from R sub L into the output. Regardless of direction, the output current is limited. For general-purpose op-amps, a typical maximum output current is about plus or minus 20 milliamperes. If R sub L is too small, absolute value of VO will decrease due to the current limit. Differential mode and common mode signals. A differential mode signal is defined as the difference between the two input signals. V sub ID equals V sub P minus V sub N. A common mode signal is defined as the arithmetic mean of the two input signals. V sub IC equals open parenthesis V sub P plus V sub N close parenthesis over 2. When the voltages at the two inputs are expressed in terms of the differential mode voltage and the common mode voltage, we have V sub P equals V sub IC plus open parenthesis V sub ID over 2 close parenthesis. V sub N equals V sub IC minus open parenthesis V sub ID over 2 close parenthesis. These two equations indicate that the common mode voltages at the two inputs are equal in magnitude and identical in polarity, while the differential mode voltages at the two inputs are equal in magnitude but opposite in polarity. When the input signal consists only of a differential mode component, the ratio of the output voltage to the differential input voltage is defined as the differential mode voltage gain. A sub ID equals V sub O prime over V sub ID. When the input signal consists only of a common mode component, the ratio of the output voltage to the common mode input voltage is defined as the common mode voltage gain. A sub IC equals V sub O double prime over V sub IC. When both differential mode and common mode components are present at the input, the output voltage is the sum of their separately amplified components. V sub O equals V sub O prime plus V sub O double prime equals A sub VD times V sub ID plus A sub VC times V sub IC. The open loop voltage gain discussed earlier refers to the differential mode gain. In practice, the common mode gain of an op-amp is extremely small, which shows that the op-amp has a strong ability to suppress common mode signals. To quantify the ability of an op-amp to amplify differential mode signals while suppressing common mode signals, the common mode rejection ratio, K sub CMR, is defined as the ratio of the differential mode gain to the common mode gain. K sub CMR equals A sub ID over A sub IC. Ideal operational amplifier. An ideal operational amplifier is obtained by idealizing each parameter of an integrated op-amp. It has the following characteristics. 1. The saturation limits of VO are equal to the supply voltages V sub plus and V sub minus. If V sub P minus V sub N is greater than 0, then V sub O equals plus V sub OM equals V sub plus. If V sub P minus V sub N is less than 0, then V sub O equals minus V sub OM equals V sub minus. In other words, the output voltage can vary only within the range defined by the positive and negative supply voltages. 2. The open-loop voltage gain of the operational amplifier is ideally infinite, with A sub VO tending toward infinity. When operating in the linear region, the output satisfies V sub O equals A sub VO times open parenthesis V sub P minus V sub N close parenthesis. Since V sub O is finite, it follows that open parenthesis V sub P minus V sub N close parenthesis equals V sub O over A sub VO, approximately 0, meaning V sub P approximately equals V sub N. This indicates that the voltages at the two input terminals are nearly equal, as if the inputs were short-circuited. This phenomenon is called a virtual short. 3. The input resistance R sub I tends toward infinity, so there is no current into the two inputs, i.e., I sub P is almost equal to 0 and I sub N is almost equal to 0. This is called a virtual open. 4. The output resistance R sub O is approximately 0. 5. The common mode voltage gain is 0, and the common mode rejection ratio is infinite, i.e., A sub VO for the common mode component is 0 and K sub CMR is almost equal to infinity. 6. The open loop bandwidth B sub W tends toward infinity. 7. The output current is unlimited. In this way, the practical model is equivalent to the ideal model, and the slanted line of the practical transfer curve is equivalent to an ideal vertical line. Introducing the ideal op-amp greatly simplifies op-amp analysis, and practical values are very close to the ideal values. Therefore, in most cases, using the ideal model to analyze op-amp circuits introduces only small errors, and the conclusions agree with practical circuits. In the linear region, the characteristics derived from the ideal op-amp, virtual short and virtual open, are very important for analyzing and designing various linear application circuits built around op-amps, and must be mastered proficiently. That concludes today's lesson. Thank you for watching. Thank you. everyone.